Here we go with the first set of video notes for homeostasis and transport. This set of video notes is going to be on osmosis and diffusion. So we'll start off a little bit with some refresher. Homeostasis, we've been talking about this a lot. Homeostasis literally means same state. Homeo means same, stasis means state, or a stable set of internal conditions. So the most popular example, of course, would be body temperature. Right? Most humans, on average, are 98.6 degrees Fahrenheit, 30 degrees Celsius. We also talked in class, there's a lot of other examples of homeostasis, like hydration, keeping the same amount of water or the adequate amount of water in your body, food or nutrition, having enough calories to get you through the day. Blood pressure could be an example of homeostasis, pH in your bloodstream. There's so many examples in addition to just temperature. But we're going to be focusing a lot on homeostasis in this unit and how cells struggle to maintain homeostasis in different environments. So it's good that we brush up on this a little bit. In a little bit more review, this time the cell membrane, which we talked about in our last unit, our cell unit, also called the phospholipid bilayer, because if you recall, each of these little guys over here is known as a phospholipid. So this is one phospholipid, and they come in a bilayer because there's two of them. So this is a phospholipid bilayer, and we learned last time that they help to maintain homeostasis. They keep things in and out of the cell. If you grabbed an image packet, this is one of the images that's in that image packet, so you could attach this next to those notes somewhere, or maybe as a fold-out over them, whatever works for you. Remember that it's selectively permeable, the cell membrane is, so it's selective about what can get through. So some things are able to make their way through these little holes, and some things cannot. Some things bounce off and can't make their way through. The things that can get in are small non-polar molecules, so they're small enough that they can get through, and they're not polar, so they don't have a charge, so they don't have to worry about being repelled like magnets. You know how they repel each other if you turn them around. Items that can't get through the cell membrane are polar molecules because they have a charge, so they just bounce off, or larger molecules, which isn't on here but should be. Large molecules as well just can't fit through these little spaces here. An exception to this would be water. Remember, water is a polar molecule, but because water is a very, very small molecule, it can easily fit through these spaces. Alright, on from our review. So what we're going to be talking about throughout this next unit is basically transport, how things move mostly in or out of a cell. And there's a couple different types of transport. You have passive transport, that's types of transport that have no energy. So diffusion, osmosis, and facilitated transport are all examples of passive. If you don't know what those are yet, that's fine, we're going to be talking about them. And the opposite of passive is active. So these are types of transport that do need to use energy. And we're going to be talking about cell membrane pumps as items that require energy, as well as endo and exocytosis. Both of these types of transport are active transport. So first I want to talk about diffusion, and I'm going to kind of give you the long version of this definition just because a lot of standardized tests really like to use the definitions of diffusion and osmosis, so I think it's important that you guys have heard it before. But diffusion is the movement of molecules, so any type of molecule, from areas of high concentration to areas of low concentration, moving down what we call the concentration gradient. So it's basically moving from areas where there's a lot of stuff to areas where there's not a lot of stuff. All right. Very, very similar to that is osmosis. Osmosis is really just a special case of diffusion. So in this case, it's the movement of water from an area of high concentration to an area of low concentration down the concentration gradient. And both of these work because all molecules really are in constant motion. Everything has a little bit of motion to it. Even things that seem solid to us, the molecules are moving a little bit, and those small vibrations cause them to move around, basically. So very central to that definition of osmosis and diffusion was the term concentration gradient. What the heck is a concentration gradient? I like to say that a concentration gradient is like a slide. If you're going to go down the slide, you don't need to use any energy, right? You just sit your butt up top, and once you push yourself down, down the slide you go, no energy needed. Okay, so we're going to talk about a couple of special examples of this. And yes, you should draw these 3 beakers here in your notes and draw the dots, roughly the same areas where I have the dots. So you might want to pause it and go ahead and draw your dots. Okay, so now that you have your beakers drawn, I'm just going to draw a little line that's basically dividing, almost like an imaginary line, dividing these beakers in half. Because we want to talk about how these things are going to work on different halves of the beakers. So each of these little dots is going to represent like a dye molecule, so maybe like a drop of food coloring. All right, so if we were to imagine this beaker divided into 2 sides, and we come over here to this beaker on the very far left, all right, and we look at this one, the concentration of dye molecules on this side is very, very, very high. It's a 10 out of 10, let's say. And this side, over here, the concentration of dye molecules is very low, so it's going to be a 0 out of 10. And this is where that slide comes in. If we were to connect those 2 lines, woo, we got a nice steep slide. Right? Very steep slide means things move very, very quickly. So these dye molecules would move relatively quickly down the concentration gradient, so from areas of high concentration to areas of low concentration. Right? Now, that's not to say that they're all just going to move down to this corner because they're going down a slide, but no, they're just moving from high concentration to lower concentration. Okay. Now if we look at the beaker over here, we have a slightly different situation. Now we've got 1, 2, 3, 4, 5, 6, 7. All right, so now it's not as high, and now we have 3 dye molecules on this side. So we're going to go up to a scale of 3, and we can draw our slide still, but now the slide isn't as steep. Right? So which slide is going to be more exciting and more thrilling? Well, this one here, because you're going to go faster. Same idea. Here, the difference between high and low concentration isn't as great. The slide isn't as steep. There's not as much of a concentration gradient. So the dye molecules are still going to move from this side over to this side, but they're not going to move as quickly. Now if we look at this one over here, right, 1, 2, 3, 4, 5 dye molecules, so we're 5 out of 10. 1, 2, 3, 4, 5, 5, and what we have here is the world's lamest slide, right? If you were to put a marble on this slide, it might roll this way, it might roll this way, it doesn't matter, it's totally flat. So basically this is the same thing. These dye molecules can move either way. Or you could almost think of it like a seesaw, right? Right now it's perfectly level, it's perfectly balanced. As soon as one dye molecule moves over here, now we're going to be slightly out of balance, and so things are going to move back and forth to keep things balanced. So this last beaker is in a state of what we call equilibrium, where we have an equal amount of stuff in space. So this one here is in equilibrium. And that wraps up our first set of video notes on diffusion and osmosis.